All right, we're going to jump into chapter 37, which is all about relativity. So Einstein's relativity, there are actually two theories of relativity, which are fairly different theories, or at least the situations that they talk about are different. The one that we're going to talk about in chapter 37 is special relativity, and it's from two papers he wrote in 1905. It took him 11 more years to write the paper about general relativity, and that is a much more complicated theory. So special relativity, also we just call it special, deals with objects that are moving at speeds close to the speed of light, and you don't have to actually be that close to it. Anything greater than 10% the speed of light, you generally see relativistic effects, and you have to deal with, deal with special relativity. General relativity, which is sometimes just called general, but is more typically called GR, deals with the effects of mass or energy, which are interchangeable through the equation E equals mc squared, which is also from this theory. They have effects on the geometry of space-time. So he believes, he sets out in this theory that space and time are actually a four-dimensional geometry, and that mass and or energy will distort the geometry of that coordinate systems. And that this is actually the true theory of gravity, and that gravity is not a force that exists between things that have mass, that gravity is the reason you see objects orbiting around, say, the sun, is because the sun has bent the geometry of space-time, and this is the shortest path. The inertial path of anything moving near the sun is to orbit around it. It's very ugly math. We generally don't have to deal with GR unless we're dealing with things that have fairly large masses or lots of energy. But if you, in any kind of regular significant figures kind of way, if you're really, really dealing with need to know times and things like that very, very, very closely, even around the Earth, you would have to deal with GR. But we're not going to do that. Einstein, just for y'all to know, actually published 5 papers in 1905. 2 papers on special relativity, 1 on Brownian motion, 1 on the size of molecules, and 1 on the photoelectric effect, which is our next lab after interference. The photoelectric effect lab is actually, his explanation of the photoelectric effect actually won him the Nobel Prize. It's actually one of the experiments which basically leads to the understanding of quantum mechanics. So it was a big year. Anyway, so special relativity is the true laws of motion, the relationships between position like x and y, and time and acceleration and velocity. These are the actual mathematical rules of that sort of stuff. But we did a bunch of chapters in the beginning in 111, chapters 2 and 4, where we had equations for things like this. And as long as your velocity is, again, fairly low, less than c, or less than 1/10 of c, the equations we would do here were special, would actually reduce down to what we learned in chapters 2 and 4. But if you have a greater speed, then you actually do have to use relativistic equations. So let's talk about some of those things. But first, let's talk about the 2 given. So there are 2 postulates that Einstein says. 2 things he's going to say, these are the things that have to be true. He says that the laws of physics have to be the same in all inertial reference frames. There's no preferred frame. So an inertial reference frame, which we're going to write as IRFs, inertial reference frames are any coordinate system that's moving with a constant velocity. So if you're standing still, you have a constant velocity of 0, and you're in an inertial reference frame. If you were in a car, and your car was moving at a constant velocity, in other words, there's no acceleration. If there's no acceleration, then that car is also an inertial reference frame. And you could sit there and say, here's some location in my car, which is the origin, and there's a y-axis and a z-axis and an x-axis that moves off from that, the origin. As long as your inertial reference frame has as long as it has a constant velocity, it's an inertial reference frame. If it's accelerating, it's not. And we talked about this a little bit way back in chapters, probably 2, 3, or 4, about inertial reference frames. That you basically, this is sort of one of the rules, is that the laws of physics have to be true in that. Obviously, if we think about an accelerating car, and say you put your drink up on the dashboard, and then the car accelerates, it looks like your drink is falling towards you, even though there was no force acting on it. And that would be a violation of the rules of physics. That's not an inertial reference frame, though, because it's accelerating. So inertial reference frame, again, it means you have it has a constant velocity, or, of course, what that really means is that there's no acceleration. So he just says this. That's got to be true anyways. This is actually one of the things that bothered us about, or bothered me at least, about the rule back when we had this force. Right? This force on a charged particle says if the charged particle is moving with a constant velocity, there's a force acting on it. But it's saying that if it wasn't moving in a constant velocity, there wouldn't be a force. So that would be a violation of this first rule. As it turns out, of course, what it really happens at the charge in the situation where the charged particle thinks it's moving, it has this force on it. In the charged particle in the coordinate system, or the inertial reference frame, where the particle thinks it's not moving but the magnetic field is coming towards it, then what happens is we get an electric field from Faraday's law. And so then there's an electric field that causes the particle to move. Anyways, it's an old, I don't want that there. Okay, so that's our first postulate, just that the laws of physics have to be true in all inertial reference frames. And then he adds that the speed of light in a vacuum, which is c, little c, which we'll just use 3 times 10 to the 8th meters per second, that has to be the same in all inertial reference frames. The speed of light has to be the same. And these both sound really, really, really reasonable, but they're going to cause things to happen which you're going to say that can't be right. But it is. These have been tested, and what we're going to say today mathematically has actually been proven to actually occur. All right, so the first thing we're going to do, and Einstein was famous for this, for having thought experiments, and have these thought experiments. So he says, let's say we have a moving train, which is moving at velocity of train, and there's 2 observers. There's going to be observer T, who's going to be on the train, and we're going to have observer G, which is who's outside on the ground. And in this train, there's a picture of what we're trying to do. So they've actually got A and O in this book, but here's a person on the train, and here's a person standing outside the train. And the person on the train is going to do a flash of light, a pulse of light, and they're going to have it move up, and there's going to be a mirror on the roof of the train car, and then the light's going to come back down. That's what's supposed to be going on here. So light goes from the bottom of the train car up. It reflects off a mirror on the ceiling, and then it comes back down to the bottom. And the observers are going to measure the time it takes between, maybe some little laser thing can catch it or something. So they're going to measure the time it takes between, there's 2 events here, and event is a very big term for relativity, event 1 and event 2. So there's going to be the T1, which is the time when the light was emitted, and T2, the time when the light reaches the bottom. So for observer capital T here, this is what that person sees. Right here they are. They're on the train, and the train is moving. But we won't worry about that. But from their perspective, they're sitting there. And so the light goes up from the bottom, hits the mirror on the top, comes back down to the bottom. We'll say that capital D is this distance from the bottom of the train to the top of the train. And so the time it takes, T2 minus T1 in the train car's perspective, is the distance the light travels divided by c, which is how fast the light has to go. So they say, okay, well then that would be 2d over c. Really simple. Inertial reference frame 2, now this person is standing out here and they see the light. So this is the train's position when the light's emitted. This is the train's position when the light reflects off. And then this is the train's position when the light comes back down and hits the bottom of the train again. And so what they see is they see the light traveling on these slanted paths. And we call that distance S. S to get up and then S to get back down. And then the distance from here to here would be V of the train times the amount of time in this for observer G. That's how long this is, right? That's how far the train has gone in that distance. Not much time. So the time it takes this delta TG is still the distance the light travels, and it's still divided by the speed of light. And so we say, okay, that's 2s divided by c. Before we go any further, I think you can easily see that the light has gone further for G. The light has gone further for somebody standing on the ground than somebody sitting in the train. And so 2s is further than 2d, and so delta t for the train observer is not going to be the same as delta t for the ground observer. Oh, yes, delta t is greater than that. Yes, it is. And so delta t for the train, the person on the train is going to think this takes less time than a person out further. So what just happened? How did that just happen? How is this different from the classical story that we had back in chapters 2 and 4? So let's go back and remember what we think in classical. So in classical description, instead of doing this with light, let's do it with a ball. Let's replace the light with a ball that I throw up. So instead of the person having a light go up and hit the ceiling and then come back down, we're going to throw a ball up in there. And so inside the train, the ball is being thrown with some velocity b in the train, which we'll just call that. So this is the person. This is the ball's velocity in the train. Let's make this a little smaller. There. And so we still have delta t for the train is still 2d divided by the velocity of the ball in the train. It's a elastic collision, which means it's just coming back as fast as you send it up. Outside the train, for somebody in G for the ground, they're going to have a prime. The ball's velocity here, we're going to say, is v prime of the ball. And it's actually, right, we have to add the velocity of the train to it, right? This is a ball that's moving inside a reference frame. So we have to do this vector addition. The ball not only has the v ball, but it also has v train. And so it has an overall velocity of v ball prime, right? We would add the vectors and we would say, oh no, if you throw it inside something that's already moving, then it has the velocity of the reference frame and the velocity of the ball. we actually had to do this a ton of times, right? I mean, you guys do these questions where I was like, if you're swimming across the river, there's the velocity of you swimming and there's a velocity of the river. And so you add those two velocities. Right? Right. And so if you do that, and we went through and we add the train's velocity to the ball's velocity, so then we say 2s divided by this prime velocity. If I do a bunch of math, I would actually get the 2d over the ball's velocity in the reference frame, in the train. However, what Einstein says as a second postulate is that light, even if you put it into a reference frame that's moving, even though in this situation the light is inside the train and the train is moving with a velocity, this can still only happen at c. You can't add v train to it. C is c. It's not going to be c prime is c plus v train. That's a no. It's just c is c. The speed of light is the speed of light. Even if you have it in a moving reference frame, it can't go any faster. And so you have to divide 2s by just the c, not c plus velocity of the train. When you insist, which Einstein does, and it turns out the universe does too, that all observers see light travel at the speed of light, no matter the velocity of their inertial reference frames, you will get that the time that is measured by one observer is not equal to the time that is measured by another observer. This has been done experimentally with very, very small measured changes, but with very, very accurate clocks, where one clock is kept in one position. They're synchronized before they go up, and then one of them is put on a plane and flown extremely fast for a long time, and then you bring it back and the clocks don't agree. Different amounts of time have passed for the two different clocks. Mathematically, I can go through and actually figure out what this distance is, or what this time is. So the delta t for the person on the ground. Again, this is sort of the triangle of the light. So the light goes up like this, and then it comes back down like that. And then we have, this is our thing. So S is the hypotenuse of a triangle that has D on one side, and then it has VT times delta T G over 2 on the other side. This whole thing is that whole thing, but this is half of it. And so the S is equal to the square root of this side squared and that side squared. If I put that in here, so I have 2 times S over C. I can move things around. Basically, I bring my C to this side, square that, and so then I have C squared times that delta TG squared equals V times delta TG squared. That should be a VT squared. Plus 4D squared. And I can move that all around, and it gets really complicated, but what I end up with is this. Go back to my red. That delta T for the ground observer is 2D over C, and then divided by the square root of 1 minus VT squared over C. VT over C squared. But this is just, that is 2D over C. And so we can put that in there instead. So we have a fairly simple equation here that relates the time by the person measured on the train and the time measured by the person on the ground. And this term, this 1 over this radical, shows up over and over and over again in equations for special relativity. And so we usually just write it as gamma. So the delta t for the person on the ground is the delta t for the person in the train multiplied by this gamma. Sometimes V over C is called beta as well. Just to be clear, both observers are correct here. There's no actual time. One of them isn't right and the other is wrong. One of them is not being fooled or having something weird going on. They both measure this time, and that's the actual time in their inertial reference frames. And so each inertial reference frame thinks the other one is moving, right? The person on the train thinks that could easily make the argument to themselves that the observer outside the train is what's moving. So there's not an actual correct time. There's just what you measure in your reference frame. I'm going to come back and do some more on this in the next video.